I'm going to talk about improved list decoding of Reed-Solomon codes via tree packings. This is joint work with Rayleigh, Chong, Shangguan, Itzhak, Tamo, and Mary Wootters. I would like to thank Rayleigh and Itzhak Tamo for preparing the slides. So let's start with basic notions of coding theory. Code C is simply a subset of ambient vector space FQ to the n, where FQ is a finite field of size Q, and elements of C are called code words. In this talk, we only consider linear codes, which means C is a subspace of FQ to the n, and the dimension of C is denoted by K. The rate R of C is defined to be K divided by n, which is a real number between 0 and 1. It measures the redundancy of the code. The standard notion of decoding is what we call unique decoding. And here's the definition. Suppose P is a real number between 0 and 1. We say a code C is P uniquely decodable if for every vector Z, the hummingbird centered at Z with a radius P times n contains at most one code word. So if the code is P uniquely decodable, then it could correct up to P times n adversarial errors in a communication. And it's also easy to see that C is P uniquely decodable if and only if the distance between any two different code words in C is at most is greater than 2 times P times n. And the central question in coding theory is to maximize the decoding radius P and the rate R. But of course, these are two conflicting goals. So to be more precise, we want to get a better trade-off between P and R. Regarding the trade-off between P and R, we have this classical bound called the Singleton Bound. It states that if the code is P uniquely decodable with rate R, then P is at most half of 1 minus R. So this picture shows the Singleton Bound. The red area is the set of parameters that are not feasible. In particular, P can never exceed 1/2 in unique decoding. In this talk, we focus on a classical family of codes called Reed-Solomon codes. Here's the definition. So suppose alpha 1 through alpha n are elements from FQ, and k is the integer that is supposed to be the dimension of the code. We define the code C to be the set of evaluations, n tuples of evaluations, f alpha 1 through f alpha n, where f ranges over the set of polynomials of degree less than k. So this is a linear code called Reed-Solomon codes, and here are some basic facts about this code. Its dimension is exactly k, and any two different polynomials agree on less than k points, evaluation points. This means the minimum distance of the code is greater than n minus k, and the code is half of 1 minus r, uniquely decodable. But recall that the Singleton bound says that P is at most half of 1 minus r, and the Reed-Solomon codes achieve half of 1 minus r. So this means Reed-Solomon codes exactly achieve the Singleton bound for unique decoding. Next, we discuss list decoding, which is a relaxation of unique decoding. So we say a code C is PL list decodable for some integer L if for every vector Z, the hummingbird centered at Z with radius P times n contains at most L code words in C. In particular, when L equals 1, we see that P1 list decodability coincides with P unique decodability. So list decoding generalizes unique decoding. And for simplicity, when C is PL list decodable, where L is polynomial in N, we also simply say C is list decodable with radius P. And one natural question is how large we can choose parameters P and R while keeping the list size L to be small. I also want to remark that here in our definition of list decodability, we do not require the existence of an efficient decoding algorithm, computing the list of code words. We just need to have a bound for the list size. So this means our definition of list decodability is a weak definition, is a weak version, and in literature is often called combinatorial list decodability. List decoding has been well studied in the literature due to its importance. It may be seen as an interpolation between unique decoding for adversarial error models and unique decoding for random error models. And list decoding also has a lot of applications in other areas, such as complexity theory, cryptography, pseudo-randomness, algorithms, etc. We want to understand what parameters can be achieved for list decoding. There is this theorem called list-decoding capacity theorem, which shows that there exists a list-decodable code with radius p and rate r, if and only if p is approximately less than 1 minus r. To be more precise, if p is less than 1 minus r minus delta for some small delta, then there exists a code of rate r that is PL list decodable, where L is almost linear in 1 over delta. On the other hand, if P is greater than 1 minus R plus delta and C is PL list decodable, then L has to be at least 2 to the delta n, so it has to be exponentially large. For this reason, 1 minus R is the best we can hope for list decoding, and we call 1 minus R the list decoding capacity. And we have seen that for unique decoding, P is at most half of 1 minus R. In particular, it can never exceed 1/2, and this bound is achieved by Solomon codes. As for list decoding, on the other hand, the bound is 1 minus R instead of half of 1 minus R. So for small r, P can even get close to 1. Now for unique decoding, the bound is achieved by Solomon codes. So the major question is if it's true that list decoding capacity is also achieved by Solomon codes. We first take a look at the classical Johnson bound. So for the special case of Solomon codes, the Johnson bound states that Solomon codes are list decodable with radius approximately 1 minus square root of r. And in a seminal paper, Goswami and Sudan further showed that Solomon codes are in fact efficiently list decodable up to a Johnson bound. As can be seen in this picture, the Johnson bound for Solomon codes is strictly better than the unique decoding radius. However, there is still a gap between the Johnson bound and the list decoding capacity. So one can ask, do we know that Solomon codes achieve the list decoding capacity? And do we even know that Solomon codes are list decodable beyond the Johnson bound? Regarding the second question about beating the Johnson bound, there are a few negative results. In particular, Ben Session, Kopati, and Rata Krishnan show that Solomon codes whose evaluation points are chosen in a certain way could not beat the Johnson bound substantially. On the other hand, Rudra and Wootters obtained the first positive result. They show that in a certain setting of parameters, there exist Solomon codes that are list decodable beyond Johnson bound. However, they obtain such an improvement over the Johnson bound only when the rate is subconstant. So this picture shows the relation between R and P, and they obtain Rudra and Wootters obtain the improvements only in the setting where R is close to 0 and P is close to 1. So this means we are looking at the upper left corner of the graph. Now I'm ready to state our main result and compare it with other results. Let's define epsilon to be 1 minus P. It's easier to state the results in terms of epsilon instead of P. The list decoding capacity of the Singleton bound states that the rate R is at most epsilon. On the other hand, the Johnson bound states that we can choose R to be at least epsilon square. The result of Rudra and Wootters shows that there exist Solomon codes whose rate is omega of epsilon over log q times polylog 1 of epsilon. So the denominator here depends on has a factor log q, which is at least log n, and this is the reason that they improve the Johnson bound only when the rate is a subconstant. And in our paper, the main result is that there exists Ray-Solomon codes whose rate is omega of epsilon over log 1 of epsilon, independent of a field size q. So as a result, we show that we can improve the Johnson bound for epsilon up to some fixed constant. Finally, there's this beautiful follow-up paper by Ferber, Kwan, and Sauerman that improve our result and show that one can even achieve the rate that is omega of epsilon, so it matches the upper bound up to a constant factor. So the takeaway of our main result is that there exists Ray-Solomon codes with a small constant rates R that are list decodable beyond the Johnson bound. Here's a summary of the results in our paper. First, as a main result, we show that there exist list decodable Ray-Solomon codes with radius 1 minus epsilon, list size O1 of epsilon, and the rate omega epsilon over log 1 of epsilon. And curiously, our proof technique shows an interesting connection between list decoding and the notion of tree packings that is well studied in graph theory. And we also give a generalization of our list decoding results to list recovery of Ray-Solomon codes. And finally, our proof technique has an application to explicit construction of some combinatorial objects called strongly perfect hash matrices. So due to the time limit, in this talk, we will focus on the first atom, which is the result about list decoding Ray-Solomon codes. The proof of our main result is based on the approach developed by Shangguan and Tamo in the previous paper. So recall that we have this decoding capacity 1 minus r, which is an upper bound of for the list decoding radius of any code. In Shangguan and Tamo's paper, they proved a more refined upper bound, which they call the the generalized Singleton bound. It says that the radius is at most 1 minus r times L divided by L plus 1. And they also conjecture that this generalized Singleton bound is achieved by Ray-Solomon codes. And they further prove that this conjecture is true for L equals 2 and 3. And it's also true when L equals 1, because in this case, we just recover this classical Singleton bound, and we already know that Ray-Solomon codes achieve the Singleton bound. And for larger and larger L, the generalized Singleton bound gets closer and closer to the list decoding capacity 1 minus r. So if we could prove this conjecture, showing that this would imply that the list decoding capacity is indeed achieved by Ray-Solomon codes. However, so far there is no proof for this conjecture for general L. The framework of Shangguan and Tamo reduces list decoding to the problem of proving that a certain matrix called the intersection matrix has full rank. And here's an idea. So we want to show that Ray-Solomon code has a list size L. So assume that this is not true, then there exists at least L plus 1 distinct polynomials f1 through fl plus 1 of degree less than k, such that the corresponding code words are in a certain Hamming ball. And let's define Fij to be Fi minus Fj for every I and j. Then the vector consisting of all these pairwise differences must be a non-zero vector because polynomials Fi are distinct. And the elements Fij satisfy certain linear equations. One kind of linear equation has the form that Fij plus Fjk plus Fki equals 0. Another kind of equation has the form that Fij alpha equals 0 if Fi and Fj agree at evaluation point alpha. And the intersection matrix is defined to represent the set of these linear equations. And if this intersection matrix happens to have full rank, then we know that non-zero vector of non-zero solution does not exist. On the other hand, the vector consisting of this Fij is a solution, but it's non-zero, so we get a contradiction. So this reduces list decoding to proving that the intersection matrix M has full rank. Shangguan and Tamo conjectured that the intersection matrix would be of full rank with hyperability if the evaluation points of the Reed-Solomon codes are chosen randomly, and however they can only prove it when the list size is 2 or 3. And in our paper, we show that with hyperability the intersection matrix has full rank over the random choice of evaluation points, assuming an actual condition that the rows of the intersection matrices are independent in the sense that the different rows depend on different evaluation points. Now, the proof of this theorem uses the tree packing theorem proved by Tut and Nash-Williams. In general, it's not necessarily true that different rows depend on different evaluation points. Now, the naive idea of reducing to this special case is removing the rows. Namely, if we have multiple rows that depend on the same evaluation points, we simply remove all of them except one. So after removing these rows, the rows become independent. However, this would remove too many rows, and as a consequence, the result is not good enough to beat the Johnson bound. And a better idea is to first sample a subset S of the set of code words and replace the set of code words by this subset. And then we consider only the elements Fij where either I and J are in this subset, and we only consider the linear equations between these Fij. And this reduces the number of equations, but at the same time also reduces the number of variables in the linear equation system. So then we use the naive idea again, but after sampling, and we managed to show that by combining the idea of sampling and removing rows, it only costs actual factor of order O log 1 over epsilon, and this implies our main result. And the reason we need to do the sampling and the removing rows is that we don't know how to prove that the intersection matrix has full rank for the general case, only with the actual condition that the rows are independent. However, we formulate a tree packing hypergraph conjecture, which can be seen as an extension of the tree packing theorem to hypergraph. Now, if this conjecture is true, it implies that the generalized Singleton bound is achieved by Reed-Solomon codes, and in particular, it would imply that the list decoding capacity is achieved by the Reed-Solomon codes. Here's a summary of our results. So we obtained an improved list decoding of Reed-Solomon codes, and our proof shows a novel connection to graph theory, particularly to tree packings. And our technique provides a method to attack the full conjecture on Reed-Solomon codes, and it has applications to list recovery and constructing explicit, strongly perfect hash matrices. And here are some open questions. The most important question is proving the full conjectures on hypergraphs and on Reed-Solomon codes. And next question is obtaining explicit construction of such Reed-Solomon codes, because the construction in our paper is probabilistic. It depends on the choice of random choice of evaluation points. And we can further ask if there is an efficient decoding algorithm for such Reed-Solomon codes. So that's the end of the talk. Thank you for listening.